All right, good morning, everyone. Let's get started. Okay, I don't think I need to add anything to the thought. So it has been there. I trust you have looked at it and we will move right along. All right, so let's start with the circuit before us. We have gone through this exercise. We did that last week. We gave you an assignment that would have given you some further practice. So let's just spend a couple minutes and go through it. So remember now, we are looking at the current flow, yeah? And we'll be able to determine which resistors are in parallel with which by virtue of the how the current behaves. So can I have a volunteer? No volunteers? So that's Mr. McIntosh, your mic is open, so go ahead, no?
Sorry, it was an accident.
That's all right, accidents can happen. Since it's already open, go ahead.
Yeah, I'm not totally sure.
Yeah, I expect that. You're just doing the course, so that's why I say you should go ahead.
So I should give the equation.
Yeah, man. So we are looking at RT.
So
RT.
R1 is parallel to R2.
So RT is equal to, you're starting with R1.
Is parallel to R2.
R2.
Which is, they're all basically parallel. So would you put a bracket between R1 and R2?
You're asking me?
Well, yes, sir. In a sense.
All right. Okay. So let's have someone else give it a try. Thank you, Mr. McIntosh. Any other volunteer?
Yes, sir.
All right, go ahead, Mr. Clark.
RT equal, I would start with R6 in series with the rest of the circuit.
Okay, so you said RT is equal to R6 in series with the rest of the circuit, okay?
R4 is in parallel with current shift in R4. It's in parallel with the rest of the circuit. R5
All right.
It's the
So it's time for me to confess. All right, Mr. Clark? And I trust you will not be angry. All right?
No problem. Yes, sir.
It can't be done. All right? Now you tell me, what were the issues you had, Mr. Clark, in writing the equation? What was the issue you had?
All right. The current is shared between 4 and 5, so both of them are in parallel.
No. Okay, fair enough, fair enough. After the current leaves R4 and 5, what happens?
What leaves R5 share between R3 and 2. and what leaves R4 shared between R3 and 1.
And that is where your confusion was.
Yes, sir.
So at these two nodes, you had an issue.
Yes. Yes, sir.
All right. Now, the issue Mr. Clark had, which is understandable, was that you had current possibly going in that direction and that direction. So based on your analysis, you were seeing currents entering the resistor from both ends. Okay?
Yes, sir. Yes, sir.
All right. Now, general statement. Once you see that in a network, once in analyzing a network, once you run into a situation where current are entering both ends of a resistor, you end up with what we refer to as a star delta circuit. Okay? Now, I use this circuit because, of course, we see the nice triangle up top there, right? And it looks like one of these that we have here. And so we end up with a star delta network. The question is, how do we treat with it? How do we analyze our circuit? Because we don't have a choice, we still have to analyze the circuit, yeah? So how do we go about doing that when we are presented with the star delta network? Okay? So you would have had, or maybe you didn't, but anyway, so you can draw this in terms of what a star network looks like. So this is your star, and that's your delta. And we then give a statement for what we refer to as an equivalent star network or equivalent delta network. So when we say the networks are equivalent, what do we mean? All right. So once you have drawn them, the key things you're going to be looking at, are the terminals. And the terminals, you have A, B, and C. So if I'm connecting the network to, an external circuit, those are the three terminals that I would connect for the star. And if I'm connecting the delta network, we have A, B, and C. We see that the terminals are at the same place. All right? So we're going to be looking at, what do we mean by equivalent? And simply put, a delta network is equivalent to a star network if it consumes the same amount of power. So we say that a star network is equivalent to a delta network if both networks will consume the same amount of power. All right, nice and simple. So Mr. Harrison, I assume you know this already. Jomo Harrison. Assume you know all of this already.
No, sir, I'm listening, sir.
No, you don't listen to this. You're right. You're in class now. You're right. It's not about listening.
I see.
Thank you. All right. So in terms of equivalence, what we just mentioned in terms of the terminals, the connecting points for the network, we still have our A, our B, and our C. If they are equivalent, it means that if I put an ohmmeter, so here's my ohmmeter. So I'm measuring resistance. It should be, that's upside down anyway. So if I put my ohmmeter and I'm measuring resistance, if I measured it across the delta network, it would be the same as if I measured it across the terminals of my star network. Fair enough? Because it's the same terminals that I am across. So if I were to put the ohmmeter over here across AB, it will be the same resistance that I would get if it's the delta that I am across or the star. Now, based on these two networks, let's look at the star first. If I were to connect an ohmmeter across these two terminals, what would be the total resistance? Anybody?
RA plus RC.
RA plus RA plus?
RA plus RC.
No, man. Let me use a clean version. I'm putting my ohmmeter here.
Oh, sorry, sir.
RB.
RA plus RB.
RA plus RB. All right? What if I were to put the ohmmeter across the delta network? If I were to put
R2. R2.
R2, sir.
But isn't R2 connected to R1 and 3? Now, do you know how an ohmmeter works? An ohmmeter requires that you have a source. Good? And what it does is to pass a current through the network. And by passing the current through the network, it then gives you a measurement, a measure of the resistance. So I want you to think of a current leaving this ohmmeter. If it's going into the delta network, what will be the total resistance? Based on what you know about resistance equation, what would RT be equal to? Come on, talk to me. It's a simple three
R2
resistance. You know?
R1, R2 plus R3.
So it's R2. Go ahead.
Plus R1 plus R3.
They are not in series. Would that current pass through the...
It will be R2 in
Yes.
parallel with R1 plus R3.
So it's R2 in parallel with R1, which is in series with
Plus
R2.
R3.
Thank
Yeah.
you. Is there anybody who don't see that? Who's unclear about that? All right. So the current that comes here will divide between R3 and the rest of the circuit. The rest of the circuit consists of R1 in series with R3. So let's go back. So if I start with the delta circuit and I'm looking across, I'm connecting across AB, which gives us our RAB. RAB is therefore equal to, as you just said, R2 in parallel with R1 plus R3. Okay? And for the star network, as we also said, RAB would be equal to RA plus RB. But by putting the ohmmeter across those two terminals, what I am seeking to find is RAB. And we spoke earlier about the networks being equivalent. Yeah? So we can equate those two. Which means that RA plus RB is equal to R2 in parallel with R1 and 2 in series, which would be R2 product over sum. So it's R2 into R1 plus R3 over R1 plus 2 plus 3.
So you can go back to the delta network for a quick second, please.
All right. So quickly, for the delta, if I go across, I'm looking into that terminal, that pair of terminals. I have R2 in parallel with 1 and 3 in series. And for the star, it's A plus B. So if I were to then go across the other terminals, I would use the same principle. So we can extend this to the other pairs of terminals. So we have RA plus RC is equal to R3 product over sum, I get plus. Yep. And then RC plus A all right. All right. Now, we can do the analysis in terms of determining the individual resistances by simply, if we made this equation 2 and this equation 3, yes? And the first one that we wrote, we make that equation 1. I can simply do equation 1 minus equation 2 and then add it to equation 3. All right? So if you're interested, you can do that. Subtract 1 from 2 and then add it to 3. If you did that, then you'll get this. RA is equal to R1, R2 over R1 plus 2 plus 3. RB, R2, 3 over 1 plus 2 plus 3. And this is for your delta to your star. We sometimes just say delta to Y. All right. But of course, do we want to be asking you to be remembering all of these formulas? Or is there an easy way to do the analysis? Are you finished writing?
Yes, sir.
All right. So this is your delta to y. However, I want to go back to the network and just to see how we can make this determination. Yeah, we can make this determination by simply looking at the network. So here is RA, and I want the equivalent value of RA within the star network from the delta network. All right. So remember the formula. RA is 1 times 2 over 1 plus 2 plus 3. Good. So let's look at the network. RA is simply the resistance that falls between R1 and 2. And so we multiply the adjacent resistances. All right, so we multiply the adjacent resistances and add all three and divide by the sum of all three. So from what we have here, RC would simply be 1 times 3 over 1 plus 2 plus 3. RB would be R1, R2 rather, times R3 over the sum. Any questions?
Yes, sir. Can you repeat what you just said, please?
I'm just repeating the formula. Here it is. That's all I said. I just repeated the formula.
Sir, they said the sum, so you mean the sum of R1 plus R2?
R1 plus 2 plus 3.
Okay, you
The
said
sum
B,
of
sir.
all three. Hmm?
I either said B, sir, as B was in the other circuit diagram, sir. That's what I'm asking. It's still a part of the 1, 2, 3.
Here is B.
Yes, sir. All right. For example, you say R2 times R3, that equal over R1 plus R2 plus R3. So I'm saying is RB R3 a part of the 1, 2, 3, sir?
RB is of the star. ABC is from the star. 1, 2, 3 is from the delta.
Okay, all right. So yes, sir.
So we are going from delta to star.
All right, sir.
So you have taken the diagram earlier?
Never finish it completely, but most of it, sir.
If, however, we wanted to go from star to delta, all right? So R1 is equal to the sum of products divided by RB, R2, the sum of products over RC, and R3, the sum of products. So this is Y to delta. We can look back at the network and see how this would work. So you have three resistances in star, and you want to find the equivalent delta. All right, finish writing?
No, sir.
Okay, so let's go back to the network. Uh, so we now have star and we want delta. So let us say I wanted RC. So RC is what I'm interested in.
RC is in the star, sir.
So we want RC, we have the delta, which is, what did I just say?
RC is in the star.
I want R1, sorry. Thank you for that. All right, so I want R1. Okay? So if I want R1 in the delta, given the star, then I would have sum of products, RA, RB, plus AC plus BC. And I'll divide. Now, when we're going from delta to star, we spoke about adjacent resistors. When we're going from star to delta, we speak of opposite. So R1, you will be dividing by RB because it's opposite. All right, R1 is here. That's the equivalent that you want. RB is opposite to it. R2, you'd have the sum of products. Here's R2, so you'll be dividing by RC. And R3, yes, again would be the sum of products, and you'll be dividing by RA. All right, that clear? Of course, we can give
Yes,
these
sir.
formulas, but until you start using them, you're still going to be a little lost.
Excuse me, sir. Sir, can I go back 1 second, please?
So tell me what you want.
I was asking that if it's the resistor that's pushing towards the one that you're trying to find that you're going to use to divide.
No, you divide using the resistor opposite to it.
All right.
All right, take this question. Are we ready? All right, so the first thing we need to do is to identify whether or not we have star delta connections. All right, one of the things I want you to avoid it at all costs, you may end up just wasting time, is to assume because of how the resistors look that you actually have a star delta. All right? So you want to make the assessment before you spend time doing any form of transforms. So we have IS, it comes to this node, we'll have current going there, we'll have current going there. Of course, the current that goes through the 12 will come to that point, some will go there. Current that goes to the 18, some will go there. And some here. So obviously, where the 6K is concerned, you're having current possibly coming from both ends. So because of that, you know you have a star or delta network. So with that said, we now need to determine whether or not we want to use a star or delta transform. Based on what we have here, the 12, the 4, and the 6K resistors, would you agree that they look like star connected? Because you have that central point there, yes? And it connects all three. So those three would be a star. We could convert them to delta. But let's start with the easier. Resistors 12, 6, and 18 are connected in delta. All right. Now let's see where the star network, the equivalent star network would be shown. So we have those connected. We just do that. So that will be the connection for my star network. All right. And I'm going to call this 1, 2, 3. Okay. And based on the notes you wrote earlier, going from delta to star, what's the formula? If we want R1, or let's not use the circuit as yet. Just let's put the general formula. So if I wanted from a delta of RA, let me be consistent and use what we had before. R1, 2 and 3, yes? And we wanted to find RA. We know that RA is going to be equal to product of adjacent resistors over sum of resistors. Okay? So with the circuit, we're going to find resistor 1. For resistor 1, all right, we'd have 12 times 18 over 12 plus 18 plus 6. All right, so that's 12 times 18 over 36. All right, which gives us 6 ohms. Everybody comfortable with that?
No, sir. Go back to the diagram. I'm trying to pick up the resistor that you put at R1.
This is 1 up top.
Right.
All right, we have a line here, right?
Yes.
What if I were to squash that line into a point?
And it took the 12 and the 18 would be connected practically at one place.
At one point?
Yes.
So whether or not I have it as a point or a line, it's the same thing.
Yes, sir.
Because remember we spoke about lump parameter circuits before? We said the lines have no resistance, eh?
Right.
Good. So squashing it
Understand
together,
the delta. Yes.
if I squash that line into a point, you would see a triangle, eh?
I don't know if it's me freaking. Yeah, I realize the delta, what I'm not seeing is the star.
Let's That's 18, that's 12, that's 6. One, where did I put 2? 2, 3. Is that any better?
Yes, sir.
So I'm saying all we have done, where you would have had a point up here, I've just stretched it out into a line. So you would have 18, 6, and 12. It's no different.
Okay, sir.
All right?
Yes, sir.
Good. So based on that, you're not going to come back to you, Mr. Clark. Can you say you understand? So for R2, let's go back to the network. For resistance 2, what are the resistors that are adjacent to R2?
The 12 kilo ohm and the 6 kilo ohm.
Okay? So for R2, what's the formula?
12 times 6 over 12 plus 18 plus 6.
So that gives us
What do I call it?
all right? And R3, what's R3?
6 times 18 over 36.
Which gives us now the next step, and most students, I mean, one of my horrible habits is to point out to students where, based on experience, most people make errors. Yeah? But most people try to skip the next step that I'm going to speak of, and that's where they end up into problems. So I'm going to say it to you, but you know, it's going to be left up to you to decide whether or not you follow my instructions or my guidance. Most persons try to complete the analysis without redrawing the circuit. And I am suggesting strongly to you that you do not make the same mistake. So before you go any further, you're now going to redraw the network and insert the new star connected resistances. All right, so we have them 1, 2, 3. I'm going to start by drawing those 3 resistors or resistances. All right, R1, that was 6K. R2 was 2K. And R3 was 3K. Now I want us to go back to the original circuit. Let's look back at the original circuit. Yes? Here's the original. And I'm going to put some terminal points for these 3. So I'm going to call this X, I'm going to call that Y, I'm going to call that Z. So X, Y, Z. All right? I'm going to put them now back here. This was X, that's Y, and that's Z. Fair enough? Now, what is it that we have connected to X? Let's start with X. The person who has their name up as Galaxy A30, can you put your proper name for me, please? I'll ask once more. The individual who has their name displayed as Galaxy A30, please correct that and put your proper name, your full name. I won't ask you again. Anyway, all right. So what's connected to X?
Yes, sir.
Pardon?
IS.
The source.
The source. So we can now draw back the source. All right. What's connected to Y?
4K.
What is it that's connected at point Y?
4K ohm, sir.
4K.
Sorry, 4K.
And for Z?
9K.
9K, sir.
9K. All right, and these were all connected back here, right? So you had 4K and you had 9K. The question asks you to determine the power supplied by the source, yes? So now that you have converted that delta to star, all right, now that you have converted the delta to star, I want you to find, give me the equation for the total resistance. Looking at the network you now have, what will that equation be?
It's in series with the rest of the circuit.
Go again?
6 in series with the rest of the circuit.
So 6 plus,
And then the two bracket 2K plus 4K in parallel with 3K plus 9K.
So 2K what?
2K plus 4K.
No, tell me exactly what to write. So you had 6 plus open bracket, what next do I write?
All right, sir. The other branch,
No, just tell me
the other
what
branch
to
is
write.
in
So RT is equal
RT
to 6.
equals 6K plus curly bracket 2K plus 4K.
I have a problem with that. Anybody want to correct it?
Sir, 2K in series with 4K.
No, tell me exactly what to write. That you just asked me to open a bracket. What next do I write?
Sir, would it be the I don't know, 2K in parallel with 3K, sir?
No.
Open and next bracket,
Open
sir.
and next
Thank you
bracket.
very much. I open an X bracket.
The
Thank
2
you.
plus the 4.
Thank you.
You
Close
can
that
close that bracket in parallel with the rest of the circuit, which is 3 plus
No, you'd have to open another bracket. 3 plus
All right,
9.
that's what I need to see. So it's 6 plus open bracket, 2 plus 4, close bracket, in parallel with open bracket 3 plus 9. All right, so 3 plus 9 gives us 12. 2 plus 4 gives us 6. 6 in parallel with 12. Six in parallel with 12.
4, sir.
Sir, 4.
4. And then 6 plus 4. So the
10.
total resistance is 10 kilo ohms. All right. So what's the power supplied? P equal. What information do we have?
The voltage and the resistance.
We have the voltage and the resistance.
V
So P
square
is given
over
by?
V square over R.
Thank you.
V square R.
So that will be 12 squared over 10K. All right, so that's 144 over 10 milliamps. All right, 14.4. You're not seeing that. 14.4 milliamperes.
Look, milliwatt, sir.
Yeah, it looks like I need to go for lunch. Thank you. All right. So the analysis just got a little more interesting. So although we started out, writing the resistance equation, and you got some practice with that, there's going to be a limitation to that. And you may have to do some modifications to your circuit before you complete the analysis. But I guarantee you that understanding the resistance equation and just using it, to do quick analysis, you will definitely see the benefit as we continue with this module. Any questions regarding what we have done thus far?
Sir, when I asked you in the beginning that I was not seeing what you're doing, I just realized you were actually transforming the delta section into a star.
Yes.
Okay.
Sir, you can walk me through the resistance equation for the
No, sir.
in terms of
I said no.
All right.
Not. It's recorded. It was done in a lecture. Go reference the lecture. It's recorded. Go to the recording. We did that, what? A week ago? No, I'm not doing that. All right. What I want you to do now, students, go, whoops. I still don't have the tender touch for that one. I need you to go back to the network. Yes? And I want you to note that these three resistors, the 12, the 6, and the 4, or if you choose, you can use the 6, the 18, and the 9. You choose. Yes? I want you to convert either set of resistors to delta and redo the question. Obviously, it's the same set of resistors. Good? The same set of resistors. So you should be consuming the same amount of power. So go do that for me. You have 10 minutes.
Sir, can you repeat the question again?
All right. Anybody reach a solution?
Yes, sir.
Yes, sir.
Mr. Bernard?
Yes, sir.
Who said they got a solution?
I did.
Just put up your hand. Just raise your hand. Okay, Mr. Clark, you got the same answer?
Yes, sir.
Good. All right, good. Good, good. All right, thank you. Thank you. Now, I know everybody hasn't gotten it, but you're gonna practice until you do. All right, you should get the same 14.4. You'll have, well, whichever delta, whichever of the stars you converted, you'll end up with 2 sets of 2 resistors in parallel, both being in series, and then that's in parallel with a single resistor. Sounds familiar?
Yes, sir.
All right, good. So I want the other persons who have not arrived at a solution to continue. While you're doing that, take this question as practice. And in practicing this, what I recommend is that, you know, just to make sure that you understand, you may want to, first of all, convert this delta into star. Yes. Of course, the question asks you to specifically find something related to the 7K. So you wouldn't have involved the 7K. All right, so you can convert that delta. You can convert this star. Okay. So do more than one conversion, and of course, both should give you the same answers. All right. That's how you're going to get the practice done. Let me remove the markings on this. Yeah. Superposition theorem and everything that we now do from here on would be aligned with the notes that you have been instructed for the last 2 weeks to download and print and have in your folders. So a lot of what I'll be saying is already in the document, and by virtue of, you know, how you would want to stop me, etc., it will give me an indication as to whether or not you have at least accessed the document or downloaded it. All right, so let's get cracking. Superposition theorem. Okay. Don't take the question. Don't take this. I just want us to look at it and try to determine the total resistance. If I were to ask, Mr. Alexander, if I were to ask you to find the total resistance for this circuit, how do you do that? If I ask you for the resistance equation, how do you start? So RT
Sir, I'm not entirely certain, but I'll try to separate the two sides like with two loops and then I do the inside.
Taylor, how do you find the total resistance?
Sir, I would firstly put the 24 and now say that is parallel to 6.
Why you say that? Why would you say that?
Sure, because the 24 is, all right, the 6 comes before the 8, so the 24 is not in parallel with the 8. And
Yeah, well, how do you determine that? I don't know what you mean before. You didn't say after, but how do you determine this before and after thing?
Well, sir, you can see that the...
How do I see it? Tell me what I'm seeing. What am I supposed to see?
I say that it is parallel.
How you know that? All right, students. I am stressing Mr. Taylor because I want to make a bigger point. The bigger point is Mr. Taylor has decided, like many of you, I'm not only talking about him, you know, but Mr. Taylor has decided, like many of you, that what we went through for the last 2 weeks is of no significance. And so he has tried to apply his basic knowledge about electrical to what is before us. All right? So he tells me that 24 is in parallel with 6, no such thing. And the reason he's saying that is possibly because of how they are orientated. Yes? Right, Mr. Taylor?
Yes, sir.
Because you can't give me a reason. And there is no reason because they are not in parallel. Good?
Yes, sir.
Now, had either Mr. Taylor or Ms. Alexander started by saying, let us see how the current is flowing, then it would suggest to me that they at least listened to half of what was said over the past 2 weeks. I know Ms. Alexander couldn't do that because this is her first class. All right? So students, I'm saying this again for the last time, because I don't want you to waste the money that you have spent in registering for this module. If you believe you know networks, withdraw, ask for an exemption. But don't waste your time. I teach principles because I know they are necessary for you to be successful. Do I make myself clear?
Yes, sir.
Yes, sir.
I am not interested in you using whatever knowledge you believe you had in the past, because things are going to get much more difficult going forward. So let me not stress anybody else. I mean, Mr. Harrison, I'm tempted to ask you to give me the equation, but I'm just going to cut to the chase. The bottom line is you cannot write a resistance equation for this circuit, simply because you would have to be basing your analysis on the current flow. Agreed? The question, therefore, is which one of these sources would you use as reference? Which current flow are you going to be looking at? Would you be looking at the current flow from the 25 or the 35? All right, and it is for that reason that we now need to look at some other approaches in terms of circuit analysis. So once you have a circuit with 2 or more sources, the methods that we have looked at to date cannot be applied. So the basic Ohm's law can no longer be applied. All right, we now need to look at theorems and other methods of analysis. And the first one we are going to be looking at is the superposition theorem. All right. So this is a theorem that is already in your notes. So you can just highlight key parts of it. All right. So the printed notes that I sent you, this information is already there. So it says that in any linear network, which has more than one source, the current flowing through or the voltage across any branch is the sum, and this can either be the phasor sum or the algebraic sum. The point I'm making is that we can apply the theorem at this level, which, for this module, we'll only be doing phasor sums. So we can apply the phasor or algebraic sum of the current through or the voltage across that branch, resulting from each source acting independently, all others being replaced at that time by their respective impedances. Now that is a mouthful. And if it's the first time you are seeing it, you didn't understand a word I just said. All right? Because I'm not sure I understand either. But anyway, be that as it may. All right? We are now going to go through the process of how we apply the theorem as stated. Before we go there, however, in the notes that you would have gotten, you would have had some descriptions of sources. You would have had description of an independent voltage source. Yes, you would have had independent current source. And you also would have had dependent voltage and current sources. Good? So you had those definitions. For your voltage source, it tells you that it's a source that maintains a voltage across it, regardless of the current flowing through it. That's the definition you had for your independent voltage source. And for your current source, it tells you that it maintains the current regardless of the voltage across it. Fair enough? Now, in the superposition theorem, it tells you down here that sources are represented or replaced by their respective impedances. So up front, I'm telling you that for a voltage source, the internal impedance is 0. And for a current source, the internal impedance is infinity. We represent 0 impedance by a short circuit. And we represent infinity by an open circuit. So those are the key things we need to note in applying the superposition theorem. Fair enough? And you're seeing all of that in your notes. All right, now let's get cracking. So the circuit I just showed you, here's a question that is associated with it, which I now need you to write down. So in the space provided in the notes, you're going to place this question, and we're then going to go through the analysis. So I give you a minute or two just to take this down. All right, so we're just going to take the steps. You just write them in the space provided or on the additional sheets that I indicated you needed to provide. All right, so first step. You're going to select one source and you're going to replace the others with their internal impedances. So in this instance, we are selecting the 35-volt source. All right, so we select the 35-volt source. We're going to work with that one. And for the 25 volt source, I'm replacing it with its internal impedance. Now, it's a voltage source. It's an independent voltage source. So I replace it with a short circuit. All right. Next step is that we're going to determine, I mean, maybe this is overkill, but we're going to determine the magnitude and direction of the current. I could simply say determine the current that flows through the desired branch. Because current is a vector quantity, so it must be magnitude and direction, yeah? But we're emphasizing it because it is that important. So we are going to determine the magnitude and the direction. Let me just double check something here. Oh, my. I thought as much. As I spoke about them, I do recall. The notes are already in your document. So these notes that I have here are already there. So we determine the magnitude and direction of the current that flows through the desired branch as a result of the source acting alone. So for this network, yes, we then I'm using circuit reduction, but of course we don't have to. We could use a resistance equation. Yeah. So if we were to use resistance equation, let's see. Coddling, is that coddling or coding? Coddling?
Yes, sir. You're not hearing me, sir?
No, you need to speak up. We're hardly hearing it.
Okay. Yes, sir. It's coddling.
Resistance, total resistance based on what we have there.
Okay. So,
the current is leaving the 35.
yes, sir. So, let's say 30 is Please, please.
No, please speak up. We're not hearing you.
Trying. I'm shouting. I'm
All right,
shouting.
all right. Maybe there's a problem with your system. Let's find someone else. Manet?
You hear me?
Yeah. Go ahead. RT?
All right, so RT is equal to 6 in series with the rest of the circuit. 24 in parallel with the rest of the circuit. 8 in series with the rest of the circuit. And 5 in parallel with 20.
Thank you. All right. So that would be the resistance equation. And 5 in parallel with 20. That's 100 over 25. So that's 4. 8 plus 4, that's 12. 12 in parallel with 24. That's 8. And 8 plus 6, that's 14. So we are expecting 14 ohms. So I did the circuit reduction. Yeah. But because I have already introduced it to the resistance equation, I can then, we can kind of speed up on those steps. So we have here the 5 and 20 to give us 4, 4 and 8 to give us 12, 12 and 24 to give us 8. Yep. And then 8 plus 12 plus 6 to give us 14. All right. So your total resistance is 14 ohms. I'm declaring before I even go there, I'm declaring that I'll be using fractions in many instances. You're not bound to use fractions, please. But if you're using decimals, please ensure that you do not round off and round off too early and introduce unnecessary errors. Okay, so the corresponding current, which is leaving the source, is 35 over 14, which gives us 2.5 amperes. Now the theorem says that we need to find the current in each branch. So similar to what we did last week, where we then looked at how the current was divided among the branches, we will do the same with this current, this 35 over 14. So if we work backwards, looking at the resistance equation, we know the 35 over 14 would pass through the 6 because it's in series. Then we had 24, yes, in parallel with the rest of the circuit, which was 12. So all of this was 12. Good. And then we had the 5 and the 20. So those are the divisions that I'm going to be applying. So we first have the 2.5 divided between 24 and 12. So the current going through the 24 ohm, which I have denoted there as IX, will be 5 over 6, and the current going through the combination, which is the rest of the circuit, will be 10 over 6. Of course, IY is further broken down between the 5 and the 20. All right, can I move on? So IY is broken down into IZ and IR. So we have the current through the 5 ohm resistor. We have the current through the 20 ohm resistor. So we have IZ to be 2/6 and IR to be 8/6. Any questions? Is there anyone who is unsure about what we just did?
Okay, for me, sir. I just said I didn't get enough. I miss you in writing. I slip up in writing it all.
Okay.
Okay. But I understand it clearly.
Good. All right. So that is with the first source. We now go to the second source because we now have the currents from the 35-volt source through all the branches. So we can move to the 25-volt source. So from this source, once I select it, I then replace the 35-volt source with its internal impedance. All right? So for the 35-volt source here, I'm replacing it by its internal impedance. All right, so for this circuit, for the 25-volt source, we have the resistance equation, right? As we see, the current would leave the 25, goes through the 5, so it's 5 in series with the rest of the circuit, which is 20 in parallel with the rest of the circuit, which is 8 in series with 6 and 24 in parallel, all right? Which is what we have here. So RT works out to 525/41. And don't be overly concerned with the fractions. As I said, use the decimal, just ensure that you do not round off too early. Now, once we have found RT, which is 525/41, we then next find IT. Yes, which is 25 divided by RT, which gives us 41/21. Now here's the key, which is why I emphasize the point about magnitude and direction. With the 25-volt source, you note that the positive terminal is at the bottom. So it means that the current will be going downwards. So although the analysis, we weren't concerned about which direction the current was flowing, it was easy looking at it going up, you know what I mean? But in terms of the finding the currents through the other resistors, we have to know, be sure about the direction that we are considering. And in this instance, we have current going down, leaving the source. And so it would then divide to the 20 and the rest of the circuit, then divide between the 6 and the 24, and then recombine to go through the 8 ohm. So that's our IT. So if you redraw the circuit, I have given names to the various currents. So I have here IA, I have IB, IC, ID. And of course, whatever current is going here as IB would be the same current up here. All right. So we can now apply current divider. Remember, we already had the resistance equation. So we know that we are first dividing between 20 and the rest of the circuit. Yes. Then we are going to divide between 6 and 24. Because we are already familiar with the current divider rule. So small, is this too much of a bore for you? Why you're not taking notes?
Oh, no, sir, not that, sir, not that, sir.
Yeah, so please take notes. We need no observers here. If you only need to observe, then, you know, find something better to do with your time.
Sir, you could go back to the previous slide for me, please.
What do you need to see?
I think you have for RT 5 plus 320 over 41, and the total you have 525 over 41.
Mm-hmm. Yes, that's what I have.
So I'm wondering if that's a mistake or something.
I don't know. I really don't know. But you can correct it when you're through. Let's just go through this. So for IA, remember we are dividing between 20 and the rest of the circuit. All right. So we have the current, IT, times the other resistance over the sum. So we get 16 over 20 over 21. All right, and then we know that IB is then divided between the 24 and the 6, so we get IC and ID. So do we have all these currents? All right, so remember, key, we need to note the direction in which the currents are flowing. All right. Sorry about that. Once we have calculated these currents, the next step, and again, this is where a lot of persons tend to make their errors. The next step, students, is to draw what we refer to as the graph of the circuit. And the graph simply means that you're going to suppress all the components and you're just going to draw lines. So this is the graph for the circuit. And what I have done, those currents that were as a result of the 25-volt source, I put them in blue. And those that were as a result of the 35, I have them in red. So we're just going to insert these various currents in the various branches based on the calculations that we had completed. So just to link a couple of them so that you understand what we're saying. ID, yes, was the current through the 24 ohm resistor. IC was the current through the 6. Here they are. And that was with the 25-volt source. If you go back to what we did before, the 35-volt source, yes, we had IT, which was a 2.5. Good. And we also had the 5/6 going through the 24. So we are putting all of these on our graph. And from the graph, we can now determine the currents through each component. All right, and that's where we're going to end it for today. We're just going to determine the current through each component. All right, and while you well, I'm going to show the calculations, and then I'm going to ask you to just respond to your names. The other thing I need to point out, students, and I said it at the first class, I'm now repeating it, and this is the last day I'm going to say it. Please remain in the classes that you have registered, for which you have registered. So if it's for the Monday evening, you stay on in the Monday class. The other thing is that the census date is, it's this, I think it's the 28th. But anyway, I'll verify that. But after the census date, if you are not fully registered for the module, I'll remove you from both Schoology and you know, everything else. So let's ensure that you have that sorted out by the census date. Okay? All right, so for each resistor, so for the 24 ohm resistor, let's just look at that. Let's go back. The 24 is over here. We have 5/6 going down. We have 5/21 going up. Obviously, the 5/6 would be larger. Yeah. So we would subtract the 5/21 from 5/6. We get 75/126. So the current through the 24 ohm resistor is 595.24 milliamps. All right, let's respond to your name, Summit, please. Alexander.
Here, sir.
Allen, Richard Allen. Atkins, Joshua.
Yes.
Barnett. Did I get a response from Atkins? All right, Barnett.
Yes, sir.
Bernard, Raheem Bernard.
Yes, sir.
Bogle,
Yes, sir.
Rentavia. Bogle,
Yes, sir.
Burkett,
Yes, sir.
Jordan Campbell. Zachary Campbell.
Here, sir.
Malik Case. Clarky Devon.
Yes, sir.
Codling is here. Denham, Brandon Denham.
Present, sir.
Ford.
Yes, sir.
Gardner. Gibbs.
Here, sir.
Halstead.
Present, sir.
Harrison.
Yes, sir.
Hales. Matthew Hales.
Present, sir.
Hemmings. I did see
Yes,
Hemmings.
sir.
George Henry. Javoy Henry.
Yes, sir.
Hopkins.
Present, sir.
Horn.
Yes, sir.
Johnson. Jonathan.
Yes, sir.
Kelly Romain. Kelly. Lawrence. Akeem Lawrence. Martin is here. McIntosh. Josh David.
Yes, sir.
Lowell McIntosh. Lerone Miller.
Here, sir.
Maurice here. Ramsey O'Neill. Richards, Dwayne Richards, Dwayne Richards. Rogers, no. Salmon, yes. Jerome Samuels.
Yes, sir. Wayne Rogers.
Wayne Rogers is here.
Yes, sir.
Why were you in the class on Monday?
So because I wanted to reinforce some knowledge.
Well, let me tell you again, sir. Do not join my class again. If you want to reinforce, you go to the website and look at the recording. Do I make myself clear?
Yes, sir.
Samuels? Jerome? All right. So those are the currents for those
Sir, I did not
resistors.
hear my
The other
name, sir.
resistors.
Vassal.
I didn't hear my name.
The other resistors. I'm not finished. I wasn't finished. Skyers,
Here, sir.
Small, DeAndre.
Yes, sir.
Marlando Small. Smelly,
Present, sir.
Sterling Adili.
Here, sir.
Sterling Ronaldino.
Present.
Stevens, Rajon. Taylor, Javian.
Present, sir.
Thomas Olandre Thomas.
Present, sir.
David Thompson. Rashawn Thompson. Vassal.
Present, sir.
Walker, Alan Walker.
Present, sir.
Let's see. Wilmot.
Present, sir.
Okay, that's it. All right. So now that we have the
Sir, I
currents,
didn't hear my name.
Sir, I didn't hear my name either. Someone.
Same for me, sir.
I said someone. I indicated that I knew someone was here.
Sir, I didn't hear
Sir,
my
I
name.
didn't-
Who is that?
Garden, sir.
Were you registered for Schoology?
Yes, sir.
When?
Couple weeks back from the first week, sir.
Awesome. Dwayne Gordon, Alex
sir.
Reed.
Yes, sir. I'm not registered for Schoology.
Yeah, so you wouldn't hear your name.
Sir, can I have the access code and so
But
forth,
you
please?
get that from your colleagues, man. Gordon, Dwayne Gordon.
Yes, sir.
So Gordon, I called the name and you answered. I have you marked as present.
Probably did similar as present, sir, but we never answer.
Well, somebody answered for you.
All right.
All right, so what I needed to do, so now you have the currents through all the resistors. Yeah. You have for the 8, the 24, the 6, good. You also have through the sources, which of course would be the same current that's going through the resistors in those branches. Yes, so you have the currents through all the circuit. What I want you to do as an activity is to do the power balance. So you're going to find the power dissipated in each resistor. And you're going to find the power supplied. All right. And if they are equal, then you know that your analysis is correct. So the question that was raised earlier as to whether or not we made an error, you will be able to verify whether that error was made. All right. All right, thank you, Mr. Bernard. Okay, that's it.
Sir.
Yes.
Yes, sir. Welcome.
Yes, sir. With Schoology, sir,